on this thing over here. Not have to tell anybody, it's this coming Thursday. And what you need to do is you need to do the following. You need to bring your formula sheet. And I said that correctly. You can use the formula sheet from the first midterm. You can use the formula sheet from the second midterm. So if you've lost the one from the first midterm, just print it out again on Blackboard if it's still there. And bring that one. So you can bring the formula sheet from midterm 1. You can also bring the formula sheet for midterm 2. This one. That's going to be really all you need, but people sometimes think they want the other one, so bring that also. So on this thing over here, bring formula sheets on this thing from midterm 1 and 2. The other thing you also need to do is bring a calculator, a scientific type calculator, not one on your phone. So scientific type calculator, and also the Scantron, like the one we had last time. In that case, it was the 815E, that little quiz strip one. For the final exam, you need a bigger one. And as far as the exam, it's going to be the same format as last time. It's going to have 3 problems and 10 multiple choice. And most of the multiple choice are concept. However, there are a couple that you've got to do simple calculations. And as far as simple calculations, there will be things like you've got a conductor. And this conductor is in the shape of a cylinder. And on this thing over here, this cylinder is a length of maybe a meter long. And it's got a resistance value of maybe 0.5 ohms. And the diameter of the thing is 1 millimeter. And what's the resistivity for the material? Well, if you wanted to calculate something like that, you've got to use simple equations, namely that R is equal to resistivity times length over area. And if the resistance is given, if the length is given, and on this one, if you know you got a circle, that means when you're going to be doing something like that, the area you should be able to figure out that is pi squared. So that shouldn't be too bad. So there's 1 or 2 where you've got to do simple calculations. The rest are concept questions for the most part. So there's, I think, 2 of them at least, maybe 3 simple calculations. The rest concept. And as far as the calculations, most likely you could probably do those in your head. So I do. You should have to come up with values fairly close. As far as the 3 problems on the exam, there are problems on the exam. There's one involving capacitors. And as far as one involving capacitors, it could be like that one that we did in class. As far as the example, where you've got maybe 3 or 4 of them, and you've got 1, 2, 3, and 4. They're connected to a battery. And what's the equivalent capacitance? What's the charge across each one? What's the potential across each one? What's the energy stored, etc. Or it could be like that one I mentioned the other day, or way back when we started doing this, if I get rid of the resistance thing. One of the other ones that I mentioned was that on this thing over here, like the homework question, you've got 3 dielectrics. You've got kappa 1, kappa 2, kappa 3. And what's the equivalent capacitance for the whole thing? Or it could be the other one that we mentioned on this thing over here. We got a vertical parallel plate capacitor. You put a dielectric in it that's liquid. Now you rotate it so it's horizontal. And then the question is on this thing over here, if this is like maybe a 1/3 full, what is the fraction that it has to be filled with over there if you have the same capacitance? Or the other one I thought was kind of fun is most everybody is taking the 133 lab with this class. Well, one of the experiments you're doing this week is most likely current balance experiment. We're on this thing over here trying to balance things out. On this thing, basically what we're trying to do is balance out a conductor in a magnetic field. So then one of the other ones I thought might be kind of cool is to do a thing called a capacitor balance. On one end, it's like doing stuff way back in 131. On one end, you put a weight. Remember way back in 131 you did that, put weights on the other side. So on this thing over here, the other one I thought might be kind of fun was this, put a capacitor on one side. And ask for what is the magnitude of the charge that's getting to the balance. Or the other one I thought was kind of fun, since I know how much everybody likes doing three-body diagrams. The other one I thought was really fun was this. You've got a parallel plate capacitor, and depending on how creative I get, one end is fixed, the other end is attached to a spring. When you add charge to it, the spring stretches. And ask how much is it going to stretch. Or the other version of something like that, instead of this one, is, well, they get really sneaky and give you one that looks like this. Where you got springs on both sides. And when you charge it up, the springs move further, or whatever it is, all kinds of things that way. So something involving capacitors. So there's one involving capacitors. It could be one after you see the problem. We have that thing I've mentioned a couple of times when we grab the defibrillator and zap you back, because after you see it, you can't believe what's there. So there's one involving capacitors. There's one on the exam involving resistance, potentials, current densities, currents, drift velocities, etc. So on this thing over here, all kinds of goodies involving conductors. So I give you something or other on this thing over here. We got a conductor in the middle of a big long cylinder. You apply a field across the cylinder. And ask for various things like what is the resistance, the potential, current density, current, etc. And I would give you like how long the thing is. I would give you the magnitude of the field, maybe give you the resistivity of the materials, all kinds of goodies like that. So something involving current, resistance, and all kinds of goodies there. It could be something like that. Or the other one is, if I was really sneaky on this one, that one I've done once or twice, the truncated cone, where you apply potential from one end to the other end. Or instead of something like that, the other one, instead of a circle that looks like that, a truncated cone, how about one in the shape of a rectangle or a cube? So on this thing, you apply potential from that end to that end. So instead of a cylinder like this, you apply a field across conductor in the shape of a square or a rectangle. And stuff like that. And then there's a problem on the exam involving potentials. As far as the thing involving potentials, it could be like that one I mentioned a couple of times already. You've got a ring, you've got an electron out here, and this thing is released when it gets to the center of the ring, how fast is it traveling. Another one could be like that one we just did a second ago, where I mentioned this one. You've got a configuration that looks like that, and we've got point P. What's the potential at point P? Or another one involving potentials like that one we did as a homework problem, I think, or an example question. On this thing, you have a big high voltage power line, and your house is below this big high voltage power line. And on this thing over here, let's change the potential from the high voltage power line to your house. Or instead of the house, you standing out there working in the field or wherever it is. So whatever else I can come up with. Or the other one I thought was really kind of cool, there's one in the book that's really kind of neat. On this thing you got a ring. And then you got a point charge. And another point charge. Then an arc. And at the center at point P was a potential at point P. So on this thing you could do that, or if I was really sneaky, maybe another arc, So you got a big long arc, another arc, and point P, and a big circle with a potential at point P. So maybe something like that. Maybe a couple of point charges, and point P that way. So something about the potential. So it could be something like that. Or one of the other ones that, I could do that here. Another one I thought of might be kind of cool involving potentials. On this thing over here, similar to this one. One of the things that we mentioned was in terms of potentials, basically like this one and this one combined. One of the things on this one I could come up with is on this thing, you got a big potential, and now on this thing, you've got, so how about on this thing, I don't know if you paid all that close attention here, but sometimes on this one you got this big high voltage power line. and this big high voltage power line, one of the things they sometimes will do in order to flex some of the wind current is they put a little triangular shaped or diamond shaped wedge on the thing. And so when you're looking at this thing from the side, it basically looks like that. There's one on each side, helps it deflect some of the wind. Or one of the other things that sometimes we'll do is on this thing put a small little weight on it. Well, let's say on my make-believe question, this thing is carrying something like maybe 360,000 volts. Or I give you, instead of 360,000 volts, I give you the charge density. So on this thing, I give you something like lambda. There's some value, like maybe 2.6 microcoulombs per meter. And then I give you the distance from there to there, like 20 meters. Then this thing is released. It's got a particular mass, fairly small. So in this case, maybe the mass is only like maybe 1.5 grams. This thing is dropping under the influence of gravity. Because of the fact that this thing accumulates charge, because it's sitting up there, it's a conductor, we got the big old power line on this thing over here. I'm going to ask questions like on this thing over here. Maybe how long is this thing going to take to go from there down to the bottom? And now you do the same thing, only now you do it on the moon. And on the moon, the gravity is 1/6 of what it is on Earth. There's no air resistance to worry about. Wish it wasn't there anyway. And then when you do it on the moon, how long is it going to take to travel the same distance? So all kinds of things. So there's a problem involving potentials. There's one involving capacitors, one involving current resistance, current density, etc. So all kinds of things. So questions on stuff like that. Well, before everybody runs out, there is a couple of things. One, maybe.
I know.
See if I can do this now. If anybody has questions, you can send email questions or